Okay, problem 8 is a decay plus a constant rate problem. It's section 2.8 of your text, equation 2.25. And so let's look at what 2.25 is. dy dt is some rate a minus by, pardon me. All right, so the rate of change in the constant, let's put this in terms of concentration. The rate of change of the concentration with respect to time is a constant input minus a decay proportional to the current concentration. What we're looking for in this problem with administering a drug is you want the decay rate, or you want the change in concentration over time to actually be zero. So you want dy dt to be zero, which means you want A equal to by. That's when you get um, the concentration to be constant, right? So A is going to be milligrams per deciliter hour, right? Per hour is going to be how many we're putting in constantly. Well, how does that make sense? Well, this is Y is milligrams per deciliter, that's concentration. B is per hour, the rate at which we're losing stuff, right? So all of that, we know B is 0.693 over T, the half-life. And again, 0.693 is just a log of 2. Okay, so now we have A and B. And I say we have A because we know what concentration we want. A is just going to be BC, right? Whatever our C is 907.2 milligrams per deciliter, that's what A is going to be, right? That's the concentration we're adding. That's the concentration we have to stay at. So we know what A has to be, and A is the constant influx, right? A is the constant influx, and A is in this case, A is that's 0.693 over 7.019 hours times 907.2 milligrams per deciliter. Okay, so this is A, whatever that number happens to be. And we've got to use the blood volume and R to get where A is and figure out from the A and the blood volume and R what is our concentration that we need in this solution that we're putting in at a constant rate R. All right. So let's put blood volume in deciliters, 52.7 deciliters, and let's put R in deciliters, 10.12 deciliters per hour. Okay, so we have here, and I'm going to go ahead and calculate this just to make my life a little easier. 0.693 divided by 7.019 times 901.2. So 88.98. A is 88.98 milligrams per deciliter hour. All right. Okay. So we've got to get some relationship between A and V and R, right? A is the rate at which we're adding stuff in milligrams per deciliter per hour. And we've got to work back from that to the concentration. Well, let's start the other way. Whatever the concentration of the solution is, right? We need that over the volume to be right times R gets us to A, right? This is the 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 concentration in this fluid, all right? Let me go the other way. Concentration in this fluid, which is going to be in milligrams per deciliter times R, which is going to give us from milligrams per deciliter to milligrams per hour, all right? Milligrams per hour has to equal to A times the blood volume, all right? These have to be equal. The concentration of the solution that we're feeding in milligrams per deciliter times the deciliters per hour we're flowing in has to be equal to A times the blood volume, because A times the blood volume gives us our milligrams per deci that we're putting in. And so we just solve this for C in the solution, and it's A V over R. All right, you just got to get all your units right, maybe put everything in that you're supposed to. And so now we get to the end of this problem and we figured out what is the concentration in the solution that we're flowing into the patient need to be in order to get to a constant level in the patient where the change over time in the concentration of the med in the patient is 0. And that's it for this problem.